So the last section looked at, well, what if you have a system of a line and a plane? So a line and a plane existing together on a three-dimensional graph. Now we're going to look at a system of two planes. Hopefully you read through the content to get that there are three cases. If you have two planes that are parallel and distinct, they will never touch. And the important thing is if the planes are parallel, their normals, which are perpendicular to the planes, must also be parallel. So I'm going to be able to look at the normals to determine. So parallel and distinct really means no work, there's no solution. Parallel and coincident, again, we have our two planes and they're in the exact same spot, but I can start to figure this out by looking to see if the normals are parallel. If they're the same plane, there's an infinite number of solutions, but in this case, the infinite number of solutions represent every point on either of the planes. If you have two non-parallel planes, they will always intersect in a line. So there's two instances where there's an infinite number of solutions, but they are different from each other. This infinite is actually bigger because it represents all the points on a plane. And there are more points on a plane than there are on a line. But there's an infinite number of points on the line. So you have to be aware that, okay, in this infinite number solution, am I representing a plane or a line? So whenever you have a system of two planes, and our planes are going to be in scalar form, the first thing you want to do is inspect the normals. Because if the normals are parallel, either there's no solution or the planes themselves are a solution. In either case, there's not a lot of work to do. You just have to figure out what case or what's happening. So I'm going to take my two normals. So normal 1 is 2, negative 2, 5. And normal 2 is 2, 1, negative 4. These are not parallel because they are not multiples of each other. One has to be a direct multiple of the other in order for them to be parallel. So because they're not parallel, they're going to intersect in a line. So I'm expecting to get something. I can't get a unique solution where it's a single point. I'm going to have something with a parameter in it. So how we do this is we're going to try and eliminate one of the variables. So I have two x's in both equations. So I'm going to eliminate the x's. And if I didn't have the same number in front of the x's, I can multiply one of the equations in order to get the same. But I'm going to use subtraction in order to eliminate the x's. So I have negative 2y minus y is negative 3y. 5z, take away, negative 4z is positive 9z. 10, take away, 7 is 3, and that gives me 0. Now, I can work with this equation, or I'm actually going to divide it all by negative 3, just to clean it up a little bit. So I get y minus 3z minus 1 equals 0, or y equals 3z minus 1. So I didn't get a unique solution for y, but I got something for y in terms of z. Remember what the solution is. It's going to be a line. So I expect a parameter. So I'm going to let z equal my parameter. Now, you can make this anything you want. It could be s. Some people like to look ahead and put a coefficient here. I always start with just let z equal t, or whatever letters here. If I would have eliminated y, I could have let x equal to t. It doesn't matter which one, as long as you let one letter involve a parameter. Because now then, y is going to be 3t minus 1, because z is still a t. So I'm starting to form something that looks like a parametric equation for a line. Now all I need is the x. So I'm going to go up and grab one of these, 2x minus 2. Instead of y, I'm going to do 3t minus 1. And then I'm going to have plus 5z, but z is t, plus 10 equals 0. And I'm going to work and isolate x in this equation. So I get 2x is equal to negative 6t plus 5t is negative 1t. When I bring it over to the other side, it's going to be t. And 2 plus 10 is 12. When I bring it to the other side, it's going to be 12. So then I have to divide by 2, so it's going to be half t minus 6. Now again, some people look at this and don't like it, and they go back and say, well, another option is to make z equal to 2t. This is a parameter. I can do any multiple of the parameter. I can't go plus anything, but I can multiply it. Then y would be 6t minus 1, 3 times 2t. And then over here, if I work that out, I would end up with Tx equals T minus 12. It would double both of these and get rid of the fractions. Either is fine. But therefore, the solution to the system is x equals 1/2 t minus 6, y equals 3t minus 1, and z equal t. They intersect and align. So let's look at another example. And now, when you're inspecting the normals, because you always have to do that, you can write them off the side to see, or you can just look. Here, this looks like it has potential, because 4 times negative 2 is 8. But it falls apart right there. So right away, I know that these are non-parallel planes. I need to eliminate one of the variables. It doesn't matter which one I do. I'm going to multiply the first one by 2 to get the x's to match up. So then I'm going to get 8x plus 14y minus 66z plus 34 equals 0. And then I have negative 8x minus 5y plus 3z minus 7 equals 0. Because these are opposite signs, I need to add these equations to eliminate my x's. So I get 9y minus 63z. That's going to be plus 27 equals 0. I'm going to divide everything by 9 just to clean this up. So y minus 7z plus 3 equals 0. So y is 7z minus 3. I know because they're not parallel, they're going to intersect and align. So I'm going to let z equals t. Again, if I would have eliminated another variable, you can let x or y equals t, doesn't matter. But now y becomes 7t minus 3. I'm going to go back up and pick an equation. I'm going to pick this top one here that I hadn't multiplied. So I'm going to do 4x plus 7y, but y is 7t minus 3. Minus 33z is going to become minus 33t plus 17 equals 0. And I'm just going to work to isolate this for x. So 4x equals 49t, subtract 33t is going to be 16t. When I bring it over to the other side, it's going to be negative 16t. Negative 21 plus 17 is negative 4. When I pop it to the other side, it's going to become positive 4. And in this case, everything is divisible by 4. So my solution becomes negative 4t plus 1. So therefore, they intersect and align, and the solution to the system is x equals negative 4t plus 1, y equals 7t minus 3, and z equals t. So inspect your normals. If your normals are not parallel, eliminate one of the variables, set one of the remaining variables to be a parameter, and work from there. Looking at one more. 3x plus 2y minus 4z plus 7 equals 0, and negative 6x minus 8y plus 8z plus 20 equals 0. So if I look at normal 1 in this case, it's 3, 2, negative 4. Normal 2 is negative 6, negative 8, and 8. But if I divide normal 2 by negative 2, I get 3. Did I not do that right? Sorry, I'm going to change this question. I wanted one that they were parallel. Let's make this a 4y. I wrote that down wrong. So then that's going to be positive 2, and 8 divided by negative 2 is negative 4. So therefore, these are parallel planes. So now I just have to figure out, are they parallel and distinct, or are they parallel and coincidence? I'm going to do that by reducing this plane. So I can divide everything in this plane by negative 2, and I do that because I want to match the first term. So that's going to give me positive 3x, positive 2y, negative 4z, plus 10 equals, minus 10, because I'm dividing by negative 2 equals 0. So our normals are the same. What tells us if this is a distinct or the same plane as this last number? Our d's are not equal. So the d from plane 1 is not equal to the d from plane 2. Therefore, they are parallel and distinct, and there is no solution to this system. If you would have done this reduction and got the same d, and d1 equals d2, well, you're still done. Therefore, there's an infinite solution, and the planes themselves are the solution. Because remember, this is a little bit different from the infinite number of solutions when they cross in a line. So if you identify that the normals are multiples of each other, then you're just seeing what's happening. You're not really doing any solving work to figure out an equation or a representation of the solution.